I'm not really sure what the value of that resistor is. I can look up the color codes since I don't have them memorized, and I can figure out what the color codes mean that the resistor ought to be, and I'm going to measure it and I'm going to compare the two. It'll be interesting to see where we land. In order to measure resistance, the component has to be completely disconnected from the rest of the circuit. So I've gotten rid of the wiring. The LED is off. I'm just measuring across terminals 32 and 33, which is the resistor, and I'm not really sure what value resistor this is. So I will start on the 200K ohm setting. I'm not getting anything useful, so I'll try clicking down to a lower range, click down to a lower range again. This is acting like I've got an incomplete circuit. Well, that doesn't make any sense. Let's go back and check our setup for our meter. Okay, we've got two wires on the terminals for the resistor. That looks good. We've got our wires plugged in the correct locations for the meter. That alligator clip and terminal are connected, and here's the culprit. We didn't have the alligator clip and the probe connected together. So make sure when you're going to do wiring, both for a circuit and for test purposes, that you have everything connected and hooked up. Now before I can make this connection, I'm going to go back and check the meter and make sure that I'm on a reasonable range. There's no way that that protection resistor is any more than 200K. I know that from experience. So I'm going to go ahead and hook this up. And I'm getting 0.3K. Let's click down one setting and see if we get some more precision. Okay, when I click down, I get some more precision. I get 0.45. And again, if you move the decimal plate 0.3 places, that would be 450 ohms. Because I'm less than 1, a second time in a row, I can click this down to a tighter range. Now I'm getting 462. If I move the decimal point 3 places, instead of 450, I get 462 instead of 450. And because 462 is more than 200, it won't give me a reading if I go down to a smaller setting. Let's demonstrate. 1 means open circuit or it can't measure it. So I put it on the 2K range and I get 0.462. Moving the decimal point 3 places, it's actually 462 ohms. So the color code on this resistor is yellow band, and then a violet band, and then a brown band, and then a gold band. And the way I know that this is oriented in this manner is the fourth band can only be gold or silver. So that means that that has to be the right side, and that the left side has to start with yellow. This is a pretty common color code chart you might find online to describe the color bands on resistors. And we said the first band was yellow. Well, that's a 4. That means the first digit in this resistor value is 4. And we measured 462 ohms. So far that makes sense. Now the second band on the resistor clearly was violet, not blue. And violet is 7. So the second digit on our resistor would be 7. So our first two digits are 4, 7. And we measured 462 ohms, and we're getting 4, 7 for the first two digits. The third band was brown. And brown means multiply that by 10. So 47 times 10, or basically just tack a 0 on the end, 470 ohms. And our fourth band is gold. That means that the resistor value has to be accurate within plus or minus 5%. Well, the gold band means we have to be accurate within plus or minus 5%. So we do 470. So 470 times 0.05, or 5%, we can be plus or minus 23.5 ohms in this case. So 470 minus 23.5, we could be as low as 446.5 ohms and still be within tolerance. Similarly, 23.5 more than 470 is 493.5. We could be as high as 493.5 ohms on that component and still be within our 5% plus or minus tolerance. So 462 ohms, we're pretty close, and that's pretty good. In fact, if we want to find out how close are we, that's a ratio. 462 divided by 470, that's 98.2, 98.3. So 100% minus 0.98298. We're actually within, got to move the decimal point 2 places. We're within 1.7% is how far off we were. Well under the 5% that we're allowed.